Hello, and welcome to Part 4 in the module on Patterns and Frameworks for Synchronous Event Handling, Connection Establishment, and Service Initialization. In the previous parts of this module, we first described the reactor and acceptor-connector patterns, which are patterns that abstract away from event handling details in order to allow application processing to be decoupled from service initialization and connection establishment. We then talked about the ACE reactor framework and how it implements the ACE mechanisms for the reactor pattern. And then we talked about how we could apply the ACE reactor framework to our JAWS web server to provide a very simple event-driven solution. In this particular part of the module, we're going to go ahead and describe the ACE Acceptor-Connector framework and then illustrate how we can apply that to a different version of the JAWS web server. This different version is going to be a slightly different path through our pattern language we've been describing. In this particular path, we're going to still use the wrapper facade pattern in order to abstract away from the tedious and error-prone and non-portable system programming mechanisms by using nice, cohesive, more modular, object-oriented wrapper facades. We're going to apply the reactor framework to be able to decouple the event dispatching and detection and demultiplexing logic from the processing behavior of those events. And we're going to join this up with the acceptor-connector pattern in the ACE Acceptor-Connector framework in order to be able to get even further extensibility and reuse from our infrastructure. So as you'll see, even though the processing logic we do is almost identical to what we did with the previous solution, there's even less code we have to worry about to write, debug, maintain, and evolve. To motivate the ACE Acceptor-Connector framework, let's first kind of step back and talk about different types of connection-oriented networked application roles. There's two roles that are most important. The connection role, which determines how apps establish connections, and then there's also the communication role, which determines whether an app plays the role of a client or a server or both. The connection roles are typified by either being active or passive. The active side is the connector part, the passive side is the acceptor part, and then the communication role is the part that interacts irrespective of whether it was started as an active or passive role. It's also important to realize the fundamental asymmetry that exists in these connection-oriented environments. So servers often, but not always, play the passive accept role, where they listen on a particular port for someone to connect to them. Conversely, clients often, though not always, play a more active role. They are going to initiate a connection to a particular port that a server is listening on. By factoring out these different roles and responsibilities, we can greatly reduce the amount of tedious and error-prone code that has to be written by application developers and has to be ported to different platforms, has to be evolved and maintained, and so on over the life cycle. In a general, if you don't have to write it, don't write it. Leverage it from someplace else. Much less problematic and expensive down the road. So let's talk now about the acceptor-connector framework in ACE. The classes in this framework decouple the connection establishment and initialization of cooperating peer services or service handlers in a networked application from the processing performed by these service handlers once they're actually connected and initialized. So you can imagine there's a variety of reasons for doing this kind of decoupling. It reduces the amount of code, and it also gives you more flexibility from a design point of view. For example, sometimes it's the case that the servers are the active initiators of connections. Sometimes the clients are the active initiators of connections. In a web server environment, the clients are the active initiators. In other environments, say network management, it might be the servers that do that. By decoupling these roles, we can make the service handler behavior be independent from whether they're established actively or passively, which means more reuse, better architecture, easier to explain, easier to evolve. In the Acceptor-Connector framework, the applications will typically subclass from the ACE service handler base class. The ACE service handler class itself is actually a subclass of other classes, as we'll talk about. It itself inherits from things like ACE task, which inherit from other parts of ACE we'll get to later. When you inherit from a service handler, there's certain methods you typically override in order to be able to kind of clean things up, clean up the service handlers when they go away. And you also typically override some methods having to do with how you activate the service handler. an activation here corresponds to the different ways you run it once it's been created. Some of those different activation modes include reactive processing, as well as various types of concurrent processing, such as multi-threading, using thread per connection, thread pools, multi-processing, a processor pool, or a process per connection, and so on and so forth. These kinds of decisions can be left as late binding decisions in the way in which you build your system. Naturally, the particular roles and classes in ACE and its Acceptor-Connector framework follow along with the roles and responsibilities that are designated in the Acceptor-Connector pattern. So it's really easy to follow along with the framework if you know the pattern. Here is a quick synopsis of the key classes in the ACE Acceptor-Connector framework. ACE Service Handler is the core piece that embodies the application or service-specific processing logic. That's where the interesting business work gets done. Then we have the ACE Acceptor, which is the part that's a factory that creates the service handlers and gets them connected when a client goes ahead and connects to the acceptor. And then on the inverse side, we have the ACE Connector, which is the part that initializes a service handler when it connects it to a corresponding acceptor that's running somewhere else. And we'll talk through these different examples, and you'll see lots of ways in which they can be customized and applied for various use cases. Take a look at this URL if you'd like to learn more about this particular framework. And of course, there's even more discussion in the various books, the POSA 2 book and the various books on ACE. Let's now do a little bit of a deep dive into the capabilities and structure of the ACE Service Handler class. This class provides synchronous and reactive data transfer capabilities. And as you can see, it's got a bunch of interesting things going on in terms of how it's associated with other classes in ACE or other classes you might define. One of the things that the ACE Service Handler provides is an inter-process communication, or IPC endpoint, that's used to communicate with its peer connected service handler. And as it turns out, this particular peer is going to be connected by the acceptor. The service handler also codifies certain best practices related to reactive network services. So out of the box, if you do nothing else and you create a service handler subclass, it's going to be able to register itself automatically with a reactor and be driven by reactive callbacks that we talked about before. So it registers itself with its corresponding reactor when it's created, and then it can also be used to shut things down and clean up its resources, including its IPC mechanism, when it's going to be destroyed later in its life cycle. The service handlers can also participate with other concurrency models that are provided through various frameworks and patterns that are used with ACE, things like active object, half sync, half async. So we'll often end up spawning pools of threads, or we'll connect together service handlers with active objects that themselves contain pools of threads in order to be able to get more concurrent behavior if a reactive approach alone doesn't work scalably or correctly in the environment in which you're trying to use it. And it gets this capability because it inherits from something called ACE Task. And we will talk about the ACE Task framework in the next module, in next modules in the course. Not right away, but we'll cover those later. The ACE Service Handler basically gets these capabilities from ACE, and it gets a number of capabilities, in fact. It gets concurrency and queuing, synchronization, dynamic configuration, and event handling from other parts of ACE. This is a good example of how frameworks can give you quite a bang for your buck, or for your non-buck if they're open source, by being able to associate canonical control flow and canonical domain-specific structures and functionality into the infrastructure, so you don't have to write that yourself. From a commonality and variability perspective, the ACE Service Handler is going to handle the variability of the inter-process communication mechanism and the synchronization mechanism via a common API. And you can come along and customize this by instantiating templates or subclassing and overriding certain hook methods in a very convenient and consistent way. Here's a simple illustration that shows how you can use the ACE Service Handler with the ACE Reactor. This is what you get out of the box if you don't do anything to the contrary. Typically, an ACE Service Handler will register itself with an ACE Reactor when it's been created by an acceptor or a connector. And then the ACE Reactor framework will automatically call back to the handle input method in the service handler when some kind of data arrives on an endpoint that the service handler indicated it was interested in knowing about. The Reactor framework can also be responsible for initiating graceful shutdown and destruction of service handlers when they are no longer needed. For example, when the underlying connection is shut down. Once again, offloading a lot of the grubby work from application developers. The ACE Acceptor class is a factory that plays the acceptor role in the acceptor-connector pattern. Keep in mind, we're not really talking much about connectors in this particular set of slides because web servers don't really do connector roles, but there's lots of other literature and examples you can learn about the connector portions in the ACE Acceptor-Connector framework if you're so inclined. So the ACE Acceptor class decouples passive connection establishment and service initialization logic from the subsequent processing performed by a service handler once the acceptor has created and initialized it. Once again, there's a bunch of interesting things going on with this class in terms of its dependencies on other parts of ACE and other things you provide it via templates and subclassing. One thing it provides, for example, is a parameterized passive mode IPC endpoint that can be used to listen and accept connections from peers, and you can provide that as a template parameter, as we'll see when we look at the code a little bit more. There's also a number of hook methods it defines using the Gang of Four template method pattern in order to be able to automate certain steps that are used to create service handlers, accept connections into them, and then activate them to run with the appropriate type of concurrency or reactive processing model, which we'll look at. By inheriting from various parts of ACE, by inheriting, for example, from the ACE service object class, which itself inherits from ACE Reactor, and it's the ACE event handler class, you can use these acceptors with reactors. You can link them in dynamically. There's lots of things you get as part of the framework that you don't have to worry about writing yourself. From a commonality and variability point of view, the ACE acceptor is going to handle the variabilities of inter-process communication mechanisms and service handlers in a common way. So we'll see by using template instantiation and subclassing, you can deal with this variability with a common interface, which makes it really easy to do plug-and-play types of extensibility to your software components. Here's an example that illustrates the common flow of control between an ACE reactor, an ACE acceptor, and some type of service handler that was parameterized into the acceptor. What typically happens is that an acceptor will be registered with the reactor for accept events, which is one of the types of events that it knows about. And when an accept event occurs, the reactor will dispatch the acceptor's handle input hook method. This hook method on acceptor actually plays the role of the template method in the Gang of Four pattern. It plays the role of the template method in the pattern, and then it calls out to a number of hook methods itself to do the various steps in the acceptance algorithm. These three steps are making a service handler, creating one as a factory method, accepting the service handler, that is accepting the connection from the client, and then activating the service handler. And that activation step can be used to decide what type of reactive or concurrent processing will be done by the service handler. Once again, by default, it uses reactive processing. It registers back with the reactor. Let's now take a look at how this acceptor-connector implementation could be applied to JAWS. This will give you a high-level view, then we'll look at some of the code. From a high-level view, this looks almost identical to the example we'd seen before when we talked about the purely reactive-based approach. The only real difference here is that rather than defining an HTTP acceptor, or an HTTP event acceptor and an HTTP event handler, these are now done for us by the various classes in the acceptor-connector framework. So we'll have an HTTP service acceptor shown here, which inherits from ACE acceptor, register itself with a reactor. When a client connects, the reactor calls back to the handle input method of the acceptor, which does that template method processing we talked about before, to create the appropriate service handler, which then registers it itself back with the reactor. Everything is purely reactive at this point. When the client sends a GET request, the reactor calls back to the handle input method on the registered HTTP service handler, and then that goes ahead and cracks open the message, finds the appropriate content, memory maps it, and then sends it back to the client. And we'll look at the code in just a second. But the good news here is that this set of canonical interactions is very, very stylized. Once you understand it for one type of application, for a web server, you can use it for many, many other things that have nothing whatsoever to do with web services or HTTP protocol processing. So let's take a look at the code and the more detailed design. This example is going to show how to use the acceptor and service handler parts of ACE in order to implement a reactive web server. As you'll see, there's even less code that we looked at before because the ACE frameworks do almost all the heavy lifting, and you just have to fill in a couple of blanks that deals with the processing of the actual protocol that corresponds to what we're building, which is a web server. So let's start by looking at an HTTP service handler, which inherits from ACE service handler, and it's got a couple of methods there. As you can see, when it inherits from service handler, it fills in that template to use the sock stream wrapper facade and something called the null sync, which means there's no concurrency taking place in this example. We'll see later how to override that. And then what it does is it defines the handle input method. This is really the only piece of application-specific processing logic in the whole implementation. This is what, of course, is going to get called back by the reactor when the GET request arrives from the client. And as you can see, it does the canonical processing we've looked at several times before. It gets the path out of the GET request that comes in. It memory maps that path into the appropriate part of the file system and stores it in memory. And then it goes ahead and transmits the content back to the client in one operation using the mechanisms in ACE to transmit exactly n bytes. This business logic is really the only thing we have to write. Now, naturally, in real life, you would add a lot more capabilities to do perhaps servlet processing. You might do more sophisticated caching operations. You might do various things where you're going to add additional capabilities, concurrency, and so on. But for now, let's keep it simple just to focus on the patterns and how they get applied. This then is the basic service processing logic for the main program. We're leveraging a lot of things we've done before. We're using our ACE acceptor, and we're parameterizing it with the service handler we just wrote and the ACE sock acceptor to accept the connection that comes from the client. We instantiate this new HTTP service acceptor into that helper class called Reactor HTTP server that we looked at before. And then the rest of our logic is very straightforward. We instantiate the appropriate templates. We derive things and use this as we talked about. We go ahead and create the ACE reactor in order to be able to drive the event loop. We create an instance of the HTTP server daemon, passing in the reactor pointer so it registers properly and can be used to clean things up appropriately when everything shuts down later. And then we just run the server event loop, and away we go. So the nice part about this is there just isn't a lot of application-specific logic here. We're customizing the framework. We're combining the realizations of those patterns we talked about before. As we'll also see, this is going to be used for much more powerful concurrent mechanisms and much more flexible, dynamically configurable mechanisms later. And we'll get to that as we explore alternative paths through our pattern language. So to summarize this particular module, this particular part of the module, the ACE Acceptor-Connector framework decouples JAWS, connection establishment, and service handler initialization from the protocol processing for HTTP. This separation of concerns allows us to reuse large parts of our solution, be able to push that into the infrastructure so we don't have to worry about it. Somebody else can maintain it. Someone else can optimize it. Someone else can debug it. Someone else can document it, and so on. So we have the generic reusable framework portion that you see here. And then we can come along and just specialize a few pieces, the business logic for processing the GET requests, as well as the part that's going to be doing the acceptance of the connections. And that was really no real code. We were just customizing templates and a few helper classes. One of the things you'll also see by our solution approach here is we're combining both white box and black box reuse. Some parts of the white box reuse come from the use of these hook methods in the template method that drives the acceptor's key algorithm steps to create a service handler, accept something into the service handler, and then activate the service handler. Those are done in a white box-like way. You can inherit from ACE Acceptor if you want to customize any of those steps to do different things. We'll see some examples of that later. But at the same time, we also get black box reuse by being able to plug in various template parameters so that you don't really have to know a lot of the details of how things work. You just have to know what type of signatures that are expected by the templates that use these template parameters. So the end result is a very powerful solution without a whole lot of code to be written, and it gives us yet one more piece in our ever-expanding pattern language for high-performance web servers. At the heart of these framework designs are commonality and variability analysis. I've talked about a lot of stuff that took years to evolve to figure out what was fixed and what varied. And we used to go back repeatedly and refactor our designs as we came up with new insights about commonality and variability. So what you're seeing here is the product of a lot of thinking and a lot of re-engineering and refactoring. The key is not just to focus on the specific examples of what ACE is doing, but to think more broadly about a methodology for building software that's extensible and contractible and subsettable for your own application environments.